Today we're going to look at cosets and Lagrange's theorem. I'm afraid I haven't prepared my normal reading notes sheet because we're basically just going to work through everything in the chapter, and it's all good stuff in there. So I'll give a lecture today about it, taking us through Lagrange's theorem, following the treatment of the book. And I'll give some suggestions for exercises at the end. And then this Friday, we'll do a problem workshop here. We'll also take into account a few of the exercises from chapter 5 as well. So I've picked out a few good suggested exercises that I'd very like you to work on in the meantime, between now and then. But I'll mention those at the end. Okay. Any questions before we begin? Okay. So Lagrange's theorem is famous result in number theory. It's in group theory. It's our first kind of decent, proper group theoretic result that isn't just kind of looking at a bunch of different examples of groups in different situations, as we have been doing up to now. Okay? And it's quite easy to state Lagrange's theorem, and it's been suggested by things we've observed in all the examples we've looked at up to now. Okay, so we've looked at examples of groups in various settings, and we've also been looking at various examples of subgroups of those groups. It has always been the case that when we're talking about a finite group, such as one of the permutation groups or the group of symmetries of a particular object, one of the dihedral groups, or a group of integers under some modulo operation, modular addition or modular multiplication. All of these finite groups, whenever we've been looking at their subgroups, it has always been the case that the size of the subgroup is always a factor or a divisor of the size of the containing group itself. Okay? We've observed that in all the examples we've looked at, but it's also true in general for every single group. Okay? And that's basically what Lagrange's theorem says. Okay? So if G is a finite group, let's say the order of G is n, and H is a subgroup of G, then the order of H is a divisor of n. Okay. So for example, if we know that our group has order 12, then we know ahead of time the only possibilities for the subgroups are subgroups of order 1. That's always around the trivial subgroup. And so if the containing group is order 12, maybe we'll see a subgroup of order 2, maybe of order 3, maybe of order 4. There cannot be a subgroup of order 5, because 5 is not a divisor of 12. There might be a subgroup of order 6, but after 6, there are no more subgroups until you get the whole group itself, which is trivially a subgroup of itself, and that will have order 12. Now, we'll look at an important counterexample towards the end. What Lagrange's theorem does not say, it doesn't say, well, there definitely exists a subgroup for any of that particular size for any divisor of n. So just because we know for example, just because we know our group is size 12, doesn't mean there has to be a subgroup of size 6, or there has to be a subgroup of size 4, etc. It just means that whatever subgroups there are, they can only have certain orders where they are a divisor of the order of the containing group. Okay? So obviously this only applies to finite groups, although some of the machinery that's used in the proof of it, what we're going to see is cosets and so on, that is equally applicable to infinite groups as well. Okay? So we've seen this in all the examples we've looked at. It has always been the case that the subgroups have had size, just a divisor of the size of the containing group. We've seen this in all the examples we've looked at. but now we can prove it in general. Okay. Now, before we go through or any questions just about the statement of it? Everybody's clear on what it's saying. Yeah. Before we go through the technical details of introducing cosets and constructing the proof of it, we'll just give a very quick main idea of the proof. Okay. So there's a nice kind of sketch we can draw that gets across the main idea of the proof. And it's just a simple kind of Venn diagram. So here's the whole group G. Here's the subgroup H of it. Now, if we think of the elements of the group as just indicated by dots inside the group. So we've got some cloud of dots in G, which are all the elements of G. There's a subgroup, which is some subset of all the elements. We know one particular element that has to be there is the identity. Okay, so the identity has to be here inside H. And if H is not a trivial subgroup, then there'll be some other elements in there, and there'll be some other elements left outside in the rest of H. Now, we're trying to show that if the order of G is n, and the order of H is n, we're trying to prove that this must imply that n divides n, using our dividing notation from second year, i.e. n divides n. Well, the basic idea of the proof is, well, just going from what we've got here, how on earth can we prove that the number of things in H must divide the number of things in G? Well, the main idea is, well, we've got one copy of H over here, which splits off some of the elements. Now, if m is going to divide n, that means the rest of the elements here, the number of these elements must also be divisible by n. Okay? Because if m divides n, it means n, the number of elements in total, is some multiple of the number of elements in here. So it must be possible to group all the remaining elements together into groups of equal size, equal to this number of elements that we have here. Okay? So the idea of the proof is to, the technical term is partition, to partition the rest of the elements of G. I'll just put a cloud of points around, but it's supposed to be that there's the same number of points in each cell. So the idea of the proof is to produce a partition. Partition in the technical sense, we considered that briefly at the start of the course when we looked at equivalence relations. So remember, our partition of the set G is splitting up the elements of the set G into a number of distinct cells, or a number of distinct subsets. And the technical conditions of partition means that no two of these cells overlap. So they're all distinct separate cells, and every element of the main set is in one of the cells. So we aren't missing any elements out, and we're covering all the elements. So produce a partition of G using H. Now, there's nothing in the definition of a partition that says the different cells in the partition have to have the same size, but that will be the case here. Okay? And such that each cell has equal size. Each cell has equal size, and the subgroup H is one of the cells. Okay, so that's the idea of the proof. We're going to partition all the elements of G into a number of different cells. H is going to be one of the cells, and all the cells are going to have the same number of elements. So then if you count up the total number of elements, you've got m plus n plus n plus n plus n plus n. So you've got a multiple of n. Okay, so that proves the divisibility for us. Okay. Okay, now I've been referring to these cells of the partition, but the correct word to use is coset. We've got the definition here of a coset. Okay, so the left So if H is a subgroup of G, then a left coset of H in G is a subset of the form subset of G of the form. So we take an element from the set G, and it's a left coset. So we put the little element G on the left of H, and what this stands for is the set of all the products G times H, where H is something from H, where little h is something from H. Okay, so this is what a left coset is. Equivalently, or in the obvious way, you can separately define a right coset. So a right coset is where you put the element from the group on the right of the set, and then you're looking at the set of all products H times G on the right. So you H on the left and G on the right. Okay. You can play this game, you can set this proof up using either left cosets or right cosets, but you just want to choose one or the other. So the normal convention is to use left cosets in setting up this proof. Now there's a couple of examples there shown in the book, which kind of illustrate some of the features of it. So if we look at example 6.2 there, I'll just put the book here rather than bring the computer quicker. So here we're looking at the permutation group S3, the symmetric group S3. This is the group consisting of all permutations of three objects. It's also simultaneously the symmetry group of the regular triangle. Okay, it's got 6 elements in it. So the subgroup we're looking at here is this subgroup here, consisting of the identity, this 3-cycle 1, 2, 3, and the 3-cycle 1, 3, 2. If you're thinking of this group as the symmetry group of the triangle, then this subgroup is the subgroup consisting of the rotations. Okay, so this would be a rotation by 1/3 of a turn. If these are vertex labels, and that would be a rotation by 2/3 of a full turn, and you got the identity of it. So the left cosets of H in S3, well, there's only 2 of them. There's H itself, okay, and that's the left coset corresponding to, well, it corresponds to each of the elements from H itself. So if you take, as the little g, if you take one of the elements that's already in H, and you look at what you get when you look at the set of products with this element G times every element in H, in those cases, you just get the same subgroup H back again. If you take any of the elements that are not in H, then you always get the same left coset, which is the set of those 3 2-cycles. Okay? Geometrically, those are the 3 reflections of the triangle. Okay? So a couple of things to notice there. And H itself is one of the cosets. Okay? If you take any element from H already, because of the closure of condition for subgroup, all these products, if G happens to be in H, then all these products are already in H, because H is closed under the group operation. Okay? And in fact, you can obtain any element from H. So if you take an element, if you take the little g from the subgroup H itself, then you just get back the same H. So H is a left coset. And you'll also notice that the same element, little g, different elements, little g, can generate the same left coset. Okay, that's always true as well. Okay, so it's not the case that whenever you take a different little g, you always get a different left coset. Okay? Sets of the elements produce the same left coset. Now, if we briefly look at the right cosets of that same subgroup, so H here is still the subgroup consisting of the three rotational permutations, if you like, the identity, the 3-cycle, and the other 3-cycle. If we look at the right cosets, we happen to see the same thing occurring. So again, we get H as one of the right cosets, and the other right coset is the set of the 3 2-cycles. However, that feature where the set of left cosets is the same as the set of right cosets, that's not always the case. Okay, so another example, still in the same group G, group of all permutations of 3 objects. This time we're taking the subgroup, this 2-element subgroup, the identity element and one of the 2 cycles. If we look at the left cosets, we see 3 of them, K itself, this subset consisting of a 2 cycle and a 3 cycle, and then the other subset consisting of the other 2 cycle and the other 3 cycle. So those are the left cosets, where if you look at the right cosets, obviously there's a lot of computation of these, you know, to evaluate all the products and calculate the right coset and so on. But if you look at the right cosets, while again K is a right coset, so this K occurs as a right coset and K also occurs as a left coset. However, in this example, the other 2 right cosets you get, they're different to the left cosets. Okay, so the structure of the partition produced by the left cosets is not in general the same as the partition produced by the right cosets. Okay. There is and when they are the same, when your subgroup does produce the same partition, whether you use left cosets or right cosets, that is significant, and that we'll be studying that case later on, and that enables you to do some quite interesting group operations, or it allows you to study the group in quite an interesting way. But in general, we don't expect that. If you just take any old subgroup, we kind of expect the partition produced by the left cosets. There's no reason to think it will be the same as the partition produced by the right cosets. Okay. Any questions so far? Okay, we have this idea of left cosets. Remember, in this kind of quick picture idea of the proof, these left cosets are going to be the cells in this partition. So we have a couple of things to prove. We have to prove that the left cosets, that they do form a partition, so that they never overlap. Different cosets never overlap, and they also cover all the elements of G, and also that they've all got the same number of elements in them. Okay? But because the definition of coset is so nice and natural in a group theory sense, just take the subgroup, you multiply it on the left by an element, we should be able to study it in careful detail and prove all those things about the partition. So the first thing to look at is lemma 6.3. So lemma 6.3, let's have a read of it, kind of settles some kind of main useful technical results. This style of lemma is fairly common in maths. We often see it. We've introduced this new idea, this new definition of a left coset. And what this lemma is saying is that all these 5 statements, they're all kind of similar looking statements. They're all equivalent. Okay? So we have multiple different ways of phrasing the same fact or presenting the same fact. Okay? So the fact that's being presented here is we've got 2 elements of the group, little g1 and little g2, 2 elements that produce the same left coset. Okay? We saw that in the example. Sometimes when you take different elements, they can end up producing the same left coset. So that's what we're looking at here. The elements little g1 and little g2 produce the same left coset. And what the lemma is just saying, well, if that's the case, then we've got 4 other statements that are equivalent to it. 4 other different ways of phrasing that same statement. Either that their inverses produce the same right coset, that one of the cosets is contained in the other one, that one of the elements is in the left coset produced by the other element, and then that this product, when you take the inverse of one of the elements multiplied by the other element, that is in H. Okay? So all the statements involve little g1, little g2, and H. They're all just kind of different mixtures of product type statements. In fact, they're all equivalent. Okay? Now, there's no proof of this in the book. It's left as an exercise, but I think we can quickly tick off all the separate little proofs. So we'll go for a proof of this. So basically what we'll do is we'll prove that we can get from one step, we can prove that we can move from one statement to any other one. Okay. So let's assume, we'll assume the first statement. Remember, we're proving these are all equivalent. We're not trying to, prove them from nothing. So we assume one of them and then see if we can move from that to back and forwards to any of the other ones. Okay, so that's statement one. So let's see if we can prove that that's equivalent to statement two. Okay, so we'll attempt to prove statement two. So given any little h in H, you look at the element little h G1 inverse. Well, sorry. Sorry, I'm assuming. Sorry. Yeah. If we consider G1H with G1 on the left and H on the right, this must be an element of G2 times capital H, because we've assumed statement one. Okay. So that implies that there exists. That implies there exists some a little k in H, such that G1H is equal to G2K. Sorry, just notice. I need to consider G1H inverse. G1H inverse. So H inverse, if H is in the subgroup H, H inverse is equally well another element of the subgroup. So G1H inverse is an element of the left coset G1H. And if that's equal to the right coset, then G1H inverse should be an element of the left coset of G2. So there exists some element of H, calling it K, such that G1H inverse is equal to G2K. But then taking the inverse of both sides, that implies that H G1 inverse is equal to K inverse G2, i.e. that implies that H G1 inverse is an element of, so that's an inverse on the G2, then took the inverse of both sides. That implies that this element H G1 inverse is an element of the right coset corresponding to G2 inverse, that right coset of H. So we started off with any little h in the subgroup H. We were able to show that this element of the right coset of G1 inverse is contained in the right coset of G2 inverse. Okay. So in other words, the right coset corresponding to G1 inverse is contained in the right coset corresponding to G2 inverse. And similarly, using the same argument, we can prove that the right coset of G2 inverse is contained in the right coset of G1 inverse, i.e. that the two are equal. So assuming these two elements, G1 and G2, assuming they give the same left coset, But using that assumption, we're able to show that any element of the right coset corresponding to G1 inverse must be present in the right coset corresponding to G2 inverse. But there's nothing special about taking the ordering of starting with G1 and G2. So using the same argument, you can prove that the conclusion goes the opposite way around, that the right coset corresponding to G2 inverse is contained in the right coset corresponding to G1. So if both right cosets are contained in each other, in other words, they must be the same. Prove two sets are contained in each other, or subsets of each other, they must in fact be the same set. Okay. So that shows that 1 implies 2, and that's basically the style of you know, showing that these things are all equivalent. So i.e., we've shown there that 1 implies 2. The same idea shows that 2 implies 1. Because we just run the same argument, except we start with G1 inverse and G2 inverse instead. Okay. So we just switch left to right and so on. Let's look at, say, 1 implies 3, or consider the equivalence that 1 is equivalent to 3. 1 is equivalent to 2. Well, certainly 1 implies 3. That's easy to see, since if G1H is equal to G2H, that certainly implies that G1H is a subset of G2H. If the two sets are equal, certainly we can say that G1 is contained in G1H is contained in G2H. The place where you've got something to prove is going in the other direction. So assume 3. We assume that G1H is contained in G2H. Now we have to try and prove that the two left cosets must be the same. Well, notice that the element G1 itself, which we can write as G1 times the identity, this is an element of the left coset. Okay. H is a subgroup, so it contains the identity. So G1 times the identity, in other words, G1, that is in the left coset corresponding to G1. So that implies that G1 is an element of G2H, the left coset of G2, because we're assuming that the left coset is contained in the right in the left coset of G2. So there must exist some little h. There exists some little h in the subgroup H such that G1 is equal to G2 times little h. I might put, since this little h I'm talking about here is special, I think I'll put a h1, I'll put a 1 subscript on it. Okay, there's some special element of the subgroup H. It's associated to G1, so I'm going to call it H1. Okay, so some particular element in the subgroup H, I'm calling it little h1, such that G1 is equal to G2 times h1. Then any other element, let's say G2H of the left coset, we can do this kind of trick. We can say that G2 times little h is equal to G2 times h1 times h1 inverse times h. So now I'm taking a general element of the left coset corresponding to G2, which will be G2 times a little h. I'm introducing h1 inverse in the middle, so I'm not changing, because that's the identity, so I'm not changing the element. But of course, this is equal to G1, G2 H1 is equal to G1 times H1 inverse H. But that combination H1 inverse H, because H1 and little h, they're both coming from the subgroup capital H. The subgroup is closed under inverses and the group operation. So this is just an element of H. So this whole thing is an element of the left coset corresponding to G1, because it's G1 times an element from the subgroup. So what we started with here was any old general element of the left coset corresponding to G2. We proved now that it must be contained in the left coset corresponding to G2. I.e., this shows that the left coset corresponding to G2 is contained in the left coset corresponding to G1. And we started off by assuming 3. We assumed the left coset of G1 is contained in the left coset of G2. Now we've got the inclusion the other way around. The left coset of G2 is contained in the left coset of G1. So the two cosets must actually be. Okay. So we've got 1 and 3 implying each other both ways. 1 implied 3 immediately, because being a subset is just part of being equal. And if you assume one coset is a subset over the other one, actually you get that the two cosets must be equal. Okay. So we've shown 1 is equivalent to 2 and 1 is equivalent to 3. The other equivalences can be proved in a similar way. We've seen most of 1 being equivalent to 4 there, I think. The crucial step here in the proof here was showing that once you had one element being in the coset of another one, then it actually must be that the two cosets are the same. So number 4, the equivalence is mostly done and can prove 1 if and only if 5 in a similar fashion. So you should definitely try and complete the proofs of those equivalences. So it's all just a lot of messing around with the definition of the coset. But it does give us a useful number of different ways, 5 different ways of thinking about two left cosets being the same. Okay. Any question about that? Okay. So that's the kind of technical device lemma out of the way. Then we start making some progress towards the proof. Okay. So next we've got Theorem 6.4. And this says that the left cosets, or when we're saying cosets here, by implication we mean the left one. The left cosets partition G. That is, what do we need to prove there? 2 things. We need to prove that the cosets cover all of G, and secondly, that no 2 different cosets have any intersection. Either 2 cosets are different or they're the same. Okay. So first of all, if little g is an element of H, then, okay, as we've said before, you can write G. You can write that G is contained in the left coset corresponding to itself. Okay. So certainly the cosets cover G. If you look at the union of all the cosets, you'll have all of G. Okay? So every element from G is contained in one of the cosets. The coset corresponding to itself. Now we have to show that they're disjoint. Okay. So if we've got two left cosets, G1H and G2H, if their intersection is not empty, okay, the intersection of two left cosets could be empty. That's fine. That means the two left cosets are distinct, completely separate. However, if their intersection is not empty, if they overlap at all, now we have to prove that they're actually the same left coset. Okay? So that implies that there exists a G. Don't get confused here. G1 and G2 are the two elements that we're talking about, their left coset. So there exists some G such that G is an element of G1H and G is an element of G2H, i.e. there exists a H1 and a H2 such that G is equal to G1H1, that's equal to G2H2. But then we can rephrase this in either way. For instance, we could say that G1 is G2, H2, H1 inverse. We can multiply both sides of the second equation there, taking this equation, G1, H1 equals G2, H2, multiplying both sides on the right by H1 inverse, we get this. But that implies that G1 is an element of the left coset corresponding to G2. But we recognize that as one of the 5 equivalent statements from previous lemma. Okay? One element being in the left coset of another element, that implies that actually the two left cosets are the same. So if two left cosets have any intersection at all, the intersection is non-empty, they must in fact be the same. Okay? So you never have two different cosets intersecting a little bit. Okay? They're either the same or they're completely separate, disjoint. Two cosets, two left cosets, G1H, G2H are either disjoint. Disjoint means they have empty intersection, or the same. Okay, so those two things prove that the left cosets partition G. So we've got a partition, so now all we have to prove, okay, there's remember, we're assuming we're dealing with a finite group, so there's obviously a finite number of cosets. There's only a finite amount of stuff in G itself, so it has to be a finite number of cosets. So the only thing we've got left to prove now is that every coset has the same number of elements. Okay? There's nothing directly, we haven't said that explicitly yet. Okay, so we just need to prove that in order to produce the proof. So that is theorem 6.9. Theorem 6.9. All left cosets. Stated for left cosets, yeah. All left cosets have the same number of elements. Now, we know that if we're looking at the left cosets of H in G, H is itself one of the left cosets. Okay. So we actually have to prove that. So we will prove for any left coset G1H that the order of G1H, the number of elements in it, is the same as the order of H. Remember this convention, modulus of a set is the number of elements in the set. So for if we can show for any left coset, and every left coset has the same number of things in H, then all the left cosets have the same number of things. Now, what's very common in kind of set theory or group theory thing, when you want to show two sets of the same number of elements, well, you can either go in and count the elements directly and show there's 10 elements in this and 10 elements in that. Or a more general way, a more kind of systematic way of approaching that is to construct what you really need to do is construct a bijection between the sets. Construct a one-to-one and onto mapping between the sets. Okay? So we will construct a bijection, one-to-one and onto mapping from H to the left coset G1H. So we're going to define a certain map from H to G1H and prove or just observe that it's a bijection. It's one-to-one and onto. Therefore, the two sets have the same number of elements. That's kind of a conclusion when the sets are finite. If you've got a one-to-one and onto mapping between two finite sets, they must have the same number of elements. When you go to talk about infinite sets, this actually becomes the definition of saying the infinite sets have the same size. The definition of infinite sets having the same size is the existence of a bijection between them. Okay? That's how you get a grasp on talking about the number of elements in an infinite set. And that's how you first discover that there are infinite sets of different sizes. There are infinite sets for which there is no bijection between them. That's the whole beginning of infinite set theory, which Cantor started in the 19th century. So relatively recent mathematics in a way. Okay, so what is this phi? Well, it's going from H to G1H. There's really only one definition you can give it. What is phi of little h going to be? It has to be a value that's in the left coset G1H. And the only device, the only ingredient that's floating around is the element G1 itself. So the only, it's just the most natural thing. We send h to the element G1H. So that's certainly a mapping from H to G1H. Here's something in H. Here's something in G1H. We want to show that it's a bijection, that it's one-to-one and onto. And that comes out straight away. So this is injective, since if it's the case that G1 H1 is equal to G1 H2, so i.e. if this is saying that phi of H1 is equal to phi of H2, well, we can simply cancel G1 from both sides, multiply both sides by G1 inverse, and we get H1 equals H2. So that shows it's injective. You can never have two different elements of H being sent to the same element under phi. Because if phi of H1 is equal to phi of H2, it must be the case that H1 is equal to H2. And phi is clearly surjective onto. By construction, I mean, is everything in G1 capital H hit by phi? Well, yeah, because the domain is H. So when you look at all the products G1 times a little h for any H and H, you do get the whole of the codomain, which is the left coset of H. Okay? And if two finite sets have a bijection between them, a one-to-one and onto mapping between them, then they have the same number of elements. That's an interesting statement because it's like a conclusion about finite sets. Because of bijection, they have the same number of elements, but when you go to infinite sets, that becomes the definition of infinite sets having the same number of elements, the existence of a bijection between. So then we're ready to prove Lagrange's theorem. And the proof of it is really just observing that we've proved everything. Okay. So proof of Lagrange's theorem. So by the previous results, the main things to observe is that the left coset partition, G, the left cosets of H partition G, all cosets have the same number of elements, all cosets contain the order of H elements. So if you want to count the total number of things in G, you just count all the elements in each of the cells in the partition. Each of the cells contains the same number of elements. It's equal to the order of H. So the number of things in G is just that multiple of H. So the number of things in G is equal to the number of left cosets multiplied by the number of things in H. Okay? So that shows that the size of H has to be a divisor of the size of G. That's basically the proof. It's just putting everything together, all the little results. This object has a technical name. This is called the index of H in G. It's the number of left cosets of H in G. It's denoted by this notation here, GH, G colon H inside square brackets. This is the index of H in G, the number of left cosets of H in the group G. And when the group is finite, it's equal as an integer to just dividing the size of G by the size of H. So that formula for it makes sense when the order of G is finite. But as I said, this machinery of cosets, which we're setting up here to prove Lagrange's theorem, we can still talk about cosets of a subgroup of an infinite group. And sometimes for an infinite group G, sometimes the index of H in G, the number of left cosets, will be finite. So sometimes this index is a finite number, even though the size of the original group G is infinite. Okay? But for an infinite group, it wouldn't make sense to talk about the size of G divided by the size of H, because you can't divide an infinite quantity by anything. Okay? But when the group G is finite, then the index of H and G is just equal to that simple ratio. Okay? But it still makes sense to talk about the index, even though the group G might be infinite. Okay, any questions about that? So I know I went fairly quickly through it, but it is good to see the whole proof in one go. So Friday, we're going to do the problem session. Friday problems. I'm just going to direct your attention to a few problems from chapter 5. Just a few I've picked out are questions 27, 31, and 32. I haven't looked at these ones. I suggest looking at these ones. in advance of Friday if you can. As I said, there's loads of exercises there, far more than we're ever going to get a chance to discuss in class. In chapter 6, there's 4 interesting ones. I mean, they're all interesting, they're all useful, but there's 4 particular ones I'd maybe like to say something about. You know, I'll be doing well on Friday to get through all of those. But and also on Friday, we didn't get time to do it today. We want to discuss the important example counterexample to the converse of Lagrange's theorem, if you like. So when you first see Lagrange's theorem, it says every subgroup, it must be, the number of elements in it must be a divisor of G. That immediately raises the hope that, say, if the group G has 12 things, 12 elements, that there must be a subgroup of size 6. 6 divides the size. That's not what Lagrange's theorem is saying. It's saying if there is a subgroup, its size must be one of the divisors of 12. So our hopes are raised briefly that Lagrange's theorem might tell you that certain subgroups exist, but there's an important counterexample, which is that, we'll discuss it on Friday, but the A6, the alternating group of size 6, this has, sorry, is this the, no, sorry, A4. A4, the alternating group of index 4, so this is the set of all even permutations on 4 objects. This has size 12, but there is no subgroup of size 6. There's no subgroup of size 6, order 6. There's no subgroup of order 6 of A4. That's an important example that it dashes our hope for that nice result. Okay. And we'll also just make one further remark. Well, I think one of the topics we're going to end the unit with is the Celoff theorems. These are theorems that do provide a partial converse to Lagrange's theorem. Celoff theorems are ones that apply to finite groups, and it does guarantee the existence of certain subgroups. Okay. We'll discuss it in detail in due course. So the Celoff theorems do guarantee the existence of subgroups of certain sizes, certain orders, based on the prime factorization of the size of the order of the containing group. Okay? But it's important to note that Lagrange's theorem does not guarantee the existence of subgroups of certain sizes. It just says if the subgroups exist, the sizes can only come from a certain set of restricted sizes, namely all the divisors of the size of the group. Okay. Okay, I think we'll finish there. Is there any questions before we finish?